of a problem we have in many of our global resources. So it's important because it's phosphorus in particular, but it exemplifies something that comes up for a lot of other ingredients too. I'll go over all these words, you'll see it all in a minute. Most important thing that you have to say right at the top of number 21 is that phosphorus has no gas phase. Technically, there are things on Earth that make a little bit of phosphorus gas, but not biotic cycling. No gas phase. That actually makes a really interesting thing, because phosphorus can be in rocks, phosphorus can dissolve into water, phosphorus can be in living things like us, but it never gets turned into gas. If you light me on fire, a whole bunch of my ingredients will turn into smoke and gases, but actually all of my phosphorus will be left in my ashes. Here's a weird implication of that none of us would have thought until somebody points it out, and you point it out, it's like, oh, I guess that's true. Watch this. Phosphorus can chill in rocks, or it can erode from the rocks when it rains, and there it is in the water, and it can chill in the water. These are all P's. So the phosphorus can chill in the water, or, you know, the water goes downhill because gravity. And trees can drink the phosphorus out of the water. That's a tree, and that's the P in the tree. That phosphorus can be used by the plant, or it can be eaten by this monkey. People were surprised that this is a monkey. How many of you could tell that that's a monkey?
It's like a person.
Dang it. I have to change my diagram. The whole class was convinced that I drew a swastika on my whiteboard yesterday. What does that say about me? Phosphorus can chill in the rocks, or it can erode from the rocks. It can chill in the water, or it can move with the water. It can be absorbed into trees. It can be absorbed into plants. But here's the funny thing. It's basically always moving downhill. Because gravity. If you take the monkey and you throw it up the hill, then it's going to dissolve into water or tumble downhill. And you throw the trees up and then you light them on fire, the phosphorus is going to just be left over in the ashes, and then the water is going to wash them away downhill. So even if there's little bumps in the road, phosphorus comes from the rocks, gets mixed into life, and then gets carried by water and gravity down to the ocean. See what I mean by it's always moving downhill? There's never a part of the cycle that throws phosphorus up into the air. You know, the evaporation, condensation, precipitation song? There's no evaporation part. It's just the downhill part. Watch what this means. Chilling in the rocks or eroding from the rocks, chilling in the water or running downhill in the water, chilling in the trees or in the monkeys, but all that stuff eventually goes downhill. In the ocean, it gets wrapped up into food webs too. So it goes into the algae and into the krill and into the sardines and into the salmons and into the sharks. But again, in the ocean, any phosphorus which leaks from life, like a dead skin cell or fish poop that trickles down to the bottom of the ocean, please look up. All that phosphorus ends up in sediment. And you know the rock cycle, that will eventually turn back into rocks, and those rocks are going to move around, tectonic plates. They'll be exposed to the surface again. But that takes hundreds of millions of years. Yeah?
So the rock cycle is incorporated into the phosphorus cycle?
Yeah, because it has a rock phase, like it can crystallize or mineralize or whatever the word is. I think it mineralizes the word. So phosphorus can come into play for a minute, live in the water, live in the biota, but then it's going to make sediment and go back, and then we got to wait a gazillion years for those rocks to pop up. Turns out this is actually a really meaningful detail. And everybody's like, what's, like, it doesn't feel that important, but watch, this actually turns out to be really important. Phosphorus is one of the most important fertilizers. We call them the big three: nitrogen, phosphorus, and potassium, NPK. You'll hear about this later. Phosphorus is one of the most important fertilizers. It's the number 2 most important fertilizer. And that's good because it's really simple to make this fertilizer. Look at the whiteboard. You can just dig up the phosphorus, mix it with water, and you made fertilizer. There's like rocks that are rich in phosphorus, and you just like dig into those rocks and you like do some stuff and it becomes fertilizer. So humans can find rocks, humans can dig up rocks, we can grind up those rocks and we can make fertilizer. There's just one problem. We're using up a rock supply, and then when fertilizer washes into the ocean, or when farm debris washes into the ocean, or when you eat those plants and then your poop goes into the wastewater treatment facility and out to the ocean, our whole planet's phosphorus supply is a one-way stream from rocks down to the ocean. Once you flush your toilet, there's like a limited amount of phosphorus rock on the planet. And once you flush it, you're like, okay, bye, go to the ocean. See you in 300 million years. Here is the important punchline for this. We only have access to 3, 4, 5, maybe 600 years of phosphorus-rich deposits. So like, you'll die on a planet with plenty of phosphorus, your children, my grandchildren, they'll never run out of phosphorus. But the point is the same, that at some point, we're not going to be able to dig deep enough to get any more phosphorus. And at that point, humanity's stuck waiting for new rocks. We really can't line the bottom of the ocean. All the phosphorus is just in sediment down there, and it's pretty tough to get it from the bottom of the sea. It's like wet and dark down there. That's actually an interesting concept. Our society's gotten really good at building things, but they're all one-way street. Like we figured out like, oh, you can dig up this thing and you like hammer it and you can make it into these. But then eventually when you're done, like you just bury them in the ground and like I guess you gotta go dig more holes. And we're kind of just harvesting our way through the Earth's crust. And all that stuff that we harvest from the Earth's crust is kind of like slipping away from us. And we're like, okay, I'll just dig more holes. But sooner or later, you know, it gets tough to dig more holes. You don't have to quote me on the exact number for how long the phosphorus lasts, because honestly there is some debate about whether it's 3 or 4 or 5 or 600 years. But the concept is real, that there comes a time when humans will not have access to one of the most important fertilizers and we won't be able to accelerate plant growth. That's a pretty scary moment. All the hippies like me, we're big on this thing called nutrient capture, where you filter out all the wastewater to try to get all that stuff before it goes into the ocean. Fun fact, I just found out yesterday that a former student of mine went on to be an environmental scientist, and he just got this paper published yesterday about reusing wastewater and how California could gather all of this lost water volume and like the most viable way to beat the drought in the long term. I just read that last night. Had a little friendly chatter on social media about it. Okay. Speak now or forever hold your peace if you have questions about the phosphorus cycle, yes?
If you prevented the phosphorus from going into the ocean, wouldn't those like things that needed phosphorus in the ocean not be able to like maintain their cycle?
Yeah, that's a really valid point. Keep in mind that like some amount of phosphorus is naturally eroding from rocks. Like this was a natural cycle before humans came along. And so we would hope that rain still hits rocks. And I don't think that us capturing our wastewater, for example, or our agricultural runoff would completely stop phosphorus from reaching the ocean. I just wanted to point out the imbalance between us breaking rock, but we have no way to accelerate getting new rock. But yeah, you're right that is a natural ingredient. If we could somehow block all phosphorus flow to the sea, that would be pretty bad. Other vocabs or other questions on 21? Sorry, other questions on 21? We've got like 2 last study goals, and I think we've just hit that point where everybody's like, no more chemistry. And I've got 1 more topic on chemical cycling. So all of you are up to here, and you've decided I'm not going to learn anymore, but I need you to try one other thing, because this comes up forever. I left it for last on purpose. This comes up in all the future units, so it's the very last one. This is number 18. About how carbon interacts with water. You remember, we had biotic carbon up here with like an animal and a flower, and then we had abiotic carbon over here where like decomposers, leakage sometimes make rocks come back out, we accelerate 1/2 of that. The biotic and the abiotic carbon. Now, here's the water. This is hydrospheric carbon. Like carbon in relation to water. Hydrospheric. Okay. There's only going to be a couple of ingredients in this entire conversation. CO2, water, carbonic acid, calcium carbonate. 5 ingredients. And that's going to take a while, so it's not too much to handle, I promise. First, please look up. Whenever there's oxides in the atmosphere, they mix with water to make acids. That's like a rule of our atmosphere. Sulfur oxides, nitrogen oxides, carbon oxides, so they mix with water to make acids. That's a general rule. That's going to come up a lot in our class. That general rule is oxides plus water make acids. Atmospheric oxides plus water. Like this. Here's an example. CO2 and water make carbonic acid, H2CO3. That's an oxide and a water that make an acid. And this is pretty much spontaneous and it's pretty much easy. Have any of you ever done a lab where you took a little cup of distilled water and you blew bubbles into it with a straw and then you check the pH of the water and it's become acidic? Okay, well, you exhale CO2, so there you go. Oxides plus that water make acids. This is not like environmentally complicated. If you just have clean water and you go, you just blow a bunch of bubbles into it, you can just use like a plain old litmus strip and it's like acidic water and actually makes some carbonic acid. P.S. That's why all rain is a little bit acidic. P.S. That's why erosion is kind of easier than you might expect on our planet because all rain is slightly acidic anyway. Because there's always CO2 in the air, so there's always some carbonic acid in rain. So all rain's a little acidic. Did anybody here ever do a science experiment, like in the 3rd grade usually, where you bring your baby teeth and you put them in a cup of soda and they dissolve in Coca-Cola because Coca-Cola is carbonated, so it has carbonic acid, so you dissolve enamel? Anybody ever try that? If you have like little siblings, or if you can just steal the teeth of another human somehow, you can just take an old tooth and you drop it in Coca-Cola, and like the enamel will fall apart. It gets all soft and like make cavities happen. That's the carbonic acid from carbonating any beverage. Oh, fun fact! How many of you have heard of LaCroix, the flavored bubbly waters that are delicious and heavenly?
LaCroix.
Excusez-moi! LaCroix!
LaCroix.
So LaCroix, this is America. LaCroix was like a fad where a bunch of parents were trying to wean their kids from soda, and so as an alternative to giving your kid Coca-Cola, you would give them some LaCroix. And the American Dental Association, American Orthodontist Association, and American Gum Association, and all of these like medical groups issued this like totally panicked press release, like no, it's carbonated, so it's still bad for their teeth. And then all kinds of parents got pissed, and they're like, but is it good or bad? So I remember like my kids' soccer practice, like parents would show up with LaCroix, and there would be like parents yelling at parents, like, you can't give that to them, it gives them cavities. Like, but it's got no sugar, but it gives them cavities. Carbonation, carbonic acid. Okay. There was that reaction written kind of large. Now if you could please look up here, there's that same reaction written smaller, where the cloud is dropping rain through the atmosphere that has CO2, so that rain plus that atmosphere makes carbonic acid. That's the same reaction we just said. And please look up, that means that surface water has a little carbonic acid. There are many steps in this chemistry that I'm skipping. But to make a long chemistry conversation into a Band-Aid for those of you with no chemistry background, you do need to know a couple of details and then we're done. Dissolved calcium, Ca, dissolved calcium, which is Ca, interacts with that carbonic acid inside of stuff with shells or bones to make calcium carbonate, CaCO3. Anybody chemistry nerd enough to tell me if it's CaCO3 or CaCO2, calcium carbonate? I thought it was 2. Some kid convinced me yesterday that it's 3. Anybody want to correct me on that?
Inside what does it in there?
Inside of stuff with shells or bones, like all your bones are made of calcium carbonate, and like scallops are calcium carbonate, and lobster shells are calcium carbonate. And pretty much once you've made calcium carbonate, there's a bunch of stuff that will break it into smaller pieces, but not much that dissolves it. So calcium carbonate ends up in sediment at the bottom of the ocean, and that's a huge carbon sink. Carbon leaves our hydrosphere as sediment of calcium carbonate. Like sand. Calcium carbonate sand. Sediment. I have an interesting story about that calcium carbonate. First of all, everybody remembers the carbonate part is from carbonation, carbonic acid. Are we okay with the carbon part of the calcium carbonate? I've got bad news for women. Here I come to mansplain more stuff about women. How many of you have heard of osteoporosis? It means porous bones. It's an affliction of elderly people whose bones get weak, and that's by far particularly common for women, because most women on average have a couple of giant parasites through their life called babies. If you're an average American woman, you're going to have at least 2 of these humongous parasites sometime in your life. And when that thing is living inside your body, it sucks all your calcium out. So women, in the course of their life, accumulate calcium for their bones, and then they lose a bunch of calcium to build a fetus. So bros, when we get old, we've never given up our calcium. We're not likely to have osteoporosis. But ladies, when you get old, if you've had children, then you've lost significant amounts of your calcium supply to those fetuses. So get this. Women are particularly discouraged from having carbonated beverages. Can anybody imagine why a woman should not have carbonated beverages?
Because due to having babies, they're more likely to get that disease anyway, so they kind of support that process by having.
How would it support the process?
By drinking carbonated beverages, right?
What happens? Yes. If a woman drinks a carbonated beverage, how does that affect her calcium supply?
Good question.
Yeah?
Does the calcium want to like bond with the other calcium within your body and then it like extracts more?
The calcium bonds with that carbonate in your beverage. And so women, when you drink, watch me please, carbonated beverages, the calcium in your digestive system leaves your body as little tiny pieces of cracked out sand. And so women can tax their lifetime calcium supply. If they have a lot of carbonated beverages, you're giving away the calcium that you otherwise should probably store up. More bad news for women, sorry. Can't have carbonated beverages either. Okay. Calcium helps take carbon out of water. This is a huge sink. There are giant deposits of calcium carbonate at the bottom of the ocean. It's a place where a bunch of carbon leaves our hydrosphere and goes to rock. In the 1980s, there were these like bracelets and necklaces that were really common called puka jewelry, puka shell stuff. Raise your hand if you've ever seen puka shell stuff. They're like little squares of light, flimsy white shells with holes in them. They're like really common in the tropics, like the Hawaiian airports always sell them. Like when surfing culture became like pop culture, like they were really common jewelry. That's called puka shell. They're just scraps of shell. And has anybody ever been to the tropics and seen that really coarse, very light white sand? It's not heavy. Like if you go to Fiji, you can grab a bucket of sand and it weighs like not very much. Because it's all crushed up shells. That's called puka sand from grinding up corals and stuff. Please look up. That's all calcium carbonate that forms a sediment at the bottom of the ocean. Turns out a bunch of our planet's carbon interacts with the water, then gets made into shells. Those shells get crumbled into sediment of calcium carbonate. That's a big sink. That's how a lot of our carbon becomes rock. That's not the fossil fuel stuff, that's just carbon bound up in something else. Anybody want to talk to me about hydrospheric carbon? Whip out 2.4. We're almost done.
Was that at the bottom right? Say one more.
Oh yeah, that's number 24. We're getting to that right now. That's why you're taking out 2.4. And no, it doesn't say one more. You'll see in a minute. First of all, in assignment 2.4, you have this interesting list of keystone species, number 22. Back in the day, I had like 20 others. You may remember seeing this in your study guide where I crossed off a bunch of keystone species, but there are so many. It turns out that we never think stuff is useful, and when you remove it from an ecosystem, there's all these interesting. So look, I left you a few examples, like the beaver and the wolf and the salamanders and the crabs and stuff, but there's a ton of keystone species. Weird relationships, not just food web stuff. But I want to talk about number 24, because you live in Santa Barbara, and your local hometown university, UCSB, is a really big deal in science. Man, now that you're juniors, let me just make a quick little plug for something. Don't waste your money on out-of-state tuition. It's really difficult to find a better science school than UCSB. And you already know the town, and you're like a local, and you already know where to get the good food, and you already have an easy way to do your laundry, and you don't have to waste your money on visiting your parents every now and then. And if you see them during the school year, you can spend all of your vacation time exploring the world. But if you go out of state, you're expected to come see mom and dad for all your vacation time, so you're just going to see one place. So trust me, go to UCSB. But anyway, number 24. I mentioned UCSB because one of the most important papers on this was written by my homie Steve Gaines at UCSB. One of the first schools to really study this phenomenon was UCSB. We've been putting CO2 into the air for a while. People have been worried about this for a long time. The idea that humans could change climate goes back really, really far. You'd be shocked. People predicted the rise in fossil fuel emissions leading to a rise in temperature like before World War II and stuff. This is old. And it's real, the extra CO2, blanket effect, warming, keeping more of our heat, that's real. Problems about the planet getting warm, that's serious. But here's another thing, number 24, with more CO2 in the air, we're also getting more carbonic acid in the water. And the biggest pool of water, the ocean, is acidifying quickly. Number 24 is about ocean acidification. We're going to talk about this in far greater length later in the year. But holy mackerel, here's an interesting thought. We've been concerned that our planet is warming for good reason, but most organisms have a really wide temperature tolerance. You all realize that your body will survive down to like 50 degrees with a little shivering. You know that, right? And you can go up to like 100 degrees, you'll turn red and you'll sweat, but you can go like 50 to 100 degrees. That's like a big temperature span. Like your ugly bodies can tolerate this broad range of temperatures. But shockingly, your cells cannot tolerate even a minute pH change. Temperature goes up and down all the time. pH is actually like critically consistent. If I changed your cellular pH by 1/100 of a point, you would have died. Like your nerves stop communicating. Like pH is really, really delicate. And we have changed oceanic pH by much more than that with all that extra CO2. So we're starting to see all these signs of stress where life in the ocean is struggling to survive in an increasingly acidic ocean. Number 24 is about this. If you haven't had a chance to read the article, I really think you should. Ocean acidification turns out to be a much bigger problem from the CO2 than the temperatures. It's not just the global warming. Changing the pH of the ocean has catastrophic impacts on ocean life. Fun detail, as the ocean gets more acidic, it's harder to build calcium carbonate. So it's possible that we might even make it impossible to sink that amount of carbon to sediment. Okay. I'm done with my study goals. Your moms and dads pay me to be here. Can I help you with anything on Unit 2? This is kind of the last call, then we shift gears. Yes?
Are we supposed to review that thing about upwelling?
Oh! Yes, we are. Thank you. Please look up. Upwelling is when cold water comes up to the top. Yeah, nice save. Upwelling is that thing where cold water comes up to the top. It wells up, upwelling. Water wells up. Bottom of the ocean is very cold. I believe upwelling was vocab in assignment 2.2. Yep. In assignment 2.2, upwelling is vocab. And you don't even need the drawing, but you probably need these words. Watch. When the wind blows offshore, that surface current pulls up water from the bottom. That turns out to be super important because cold water holds more nutrients. Key fact, this comes up throughout the year. Cold water holds more nutrients. So cold water is more productive. It's a better place to fish. You've got more algae and stuff. More things grow in cold water. Cold water holds more nutrients. That's why upwelling is important. If this was sand, when you blow this way, it would just pile up over here. But water levels itself because fluids and pressure and gravity. So when you push away all the surface water, that's going to draw water up from the bottom. Offshore wind makes surface current, which brings cold water up. That's called upwelling. That's important because it's more productive. You always want to fish where there's upwelling. There's more fish there. Yo.
How is that connected to like the oyster fishing thing? Talk about like.
I didn't realize that it was. Is that in the oyster fishing article?
I thought it said something about like there was an upwell in the current and then like the oysters.
I can tell you one thing I know about oysters.
Yeah, it said upwells of deep, cool offshore currents, they more acidic water, rock to surface.
Oh, interesting. So, if upwellings are more acidic, then that would definitely affect oyster production because it's tough to build calcium carbonate in acidic environments. Globally, there's been this like collapse of oyster farms because they don't grow as fast anymore. It's harder to build that calcium carbonate bond when the water's more acidic. I didn't realize that upwellings were more acidic, but if you find that in the article, I believe you. My statement was more about productivity because of dissolved nutrients, but maybe in cold water you make more acids for the same reason. Yeah. That sounds interesting. I didn't know. Sorry. What else? Thank you for reminding me about the upwelling thing. Are there any other holes in your homework packet? It's Fresno or Florida State Universities, but it also is an acronym for messing things up to FSU.
Yeah.
And so I had this long tradition when I would peek back, I would always PFSU into the snow banks on high acids. And took photographs and shared it with my homies. Okay. If we're done with the study guide, are we done with the study guide? Last call for study guide. You'll need a blank sheet of paper and you can put away your other stuff. On that piece of paper, you should write Apes unit exam scores. Because I'm about to show you your Unit 1 exam. And I often make errors in recording your scores. So, I'm about to hand out your Unit 1 work. Keep it. Keep all papers all year. I'm about to hand out your Unit 1 exam. You don't get to keep that. I need that back, test security. So if there's a mistake in the homework, you keep that, you'll catch it and you can fix it. But on this paper that you just took out, you'll have to write your Unit 1 multiple choice and free response scores. Because later on, if I recorded 25, you wouldn't have evidence other than your paper that it should be a 28 or whatever. You're going to ask me all sorts of questions when stuff comes out. I'd like you to not ask me any questions. Accumulate all your Unit 1 work. You can put that away. Keep your Unit 1 free response and your Unit 1 multiple choice. And once they're all delivered, I'll talk to you about how many points were possible, what the curve is, how to fix your grades, what the grades mean. We'll get into all that in a minute. The more volunteers I have, the faster this goes. Since I don't know many of your names, it would be better if you went out there and you could just start yelling people's names if you don't know people. come up here and help me pass out stuff. Go. Help me pass out stuff. More. Like 8 volunteers minimum. More. More.
Alright.
So what was the word? No, like what it, like if it was C2 or
Okay.
Wait, the name is Laura.
Thank you. Isabel, you can stop the stream. What's happening?